Before heading to the video, if you haven't subscribed the channel, do subscribe it and don't forget to click the bell icon for the latest update notification. If you like the video, do like, comment and share. Stay tuned with learnbay.co. Happy learning!
Recap. So here's what we're saying. We're saying that the mean of the average value of the time series is slowly changing over time, slowly changing. So there's not a lot of trend per se in the data. There could be there's absolutely absence of seasonality. So this situation is what we call as a simple exponential smoothing situation. So here we assume that you have a time series value is going to be like one constant and a random component. This constant is estimated by using half the observations, and what we do is we just calculate the mean. Okay, that's what we do in order to get this one. Over here we have something called alpha. This is called smoothing constant. Yeah. Once you have a smoothing constant, you are able to essentially update the next level. So you're going to say that alpha times yt plus 1 minus alpha, lt minus 1, and this gives me the the level of the next period. That's how I will be able to proceed. Now once you keep on, if you expand on this term, you will see that the older observations become exponentially less and less important. Exponentially less important. Okay, perfect. This is what we discussed yesterday. So we are going to talk about a couple of new cases where what if a trend is present but no seasonal pattern. The next thing is both trend as well as seasonal pattern is present. So in case where you only have trend but you don't have a seasonal pattern, we will call that as Holt's exponential smoothing, or sometimes also known as double exponential smoothing. When you have both trend and seasonality in the data, we use the Holt-Winters method. Okay, that's the agenda for ourselves today. Okay, we just did a quick recap on the other page, but over here, this is what we're talking about, that this is the updating smoothing equation for simple exponential smoothing is given by this. Alpha is a smoothing constant between 0 and 1. The forecasting is a two-step process. We do a computation with only half the number of observations, right? And then we compute the forecast for yt plus p, where we say, okay, if it is it's basically the level t actually. So with p, where p equal to 1, 2, 3, and so on, so where lt is defined here. So if you go one period ahead, yt plus 1, it's going to be again, so it's pretty much lt, because you're saying that with as period forecast changes, there is no trend, so there is no time dependent movement of the trend. We will see this change when we move to the next level, when we move to double exponential smoothing. Holt's exponential smoothing. Over here, the major difference between the simple exponential smoothing and this lies in the fact that we are going to assume that there is some trend in the data. Not actually assume, we will see that there is some trend in the data. Now, because there is trend in the data, the linear trend equation, or the linear trend that will get followed, we assume that it will be beta 0 plus beta 1 t. What this means is even before the time t equal to 0, this is the minimum level with which it starts, and this is nothing but the rate at which the value of yt changes with time. This is the rate at which the value of yt changes as time progresses. If the values of the parameters beta 0 and beta 1 are slowly changing over time, Holt's exponential smoothing method can be applied to the time series observations. When we talk about the level in the simple exponential smoothing, we had beta 0 only, right? But in this case, we will have beta 0 plus beta 1t. So it's going to be a combination. So beta 0 plus beta 1t, that will give me the level. Okay, now for the growth rate or trend, like I was saying, this is going to be beta 1, nothing but how much yt changes with time. So as time becomes 0 to 1, yt becomes beta 1. When time becomes 1 to 2, then yt will again be factored by beta 1 growth rate. So beta 1, from coordinate geometry, we know that, you know, beta 1 is nothing but the slope. So from our linear regression or ordinary least square regression, we know that beta 1 is the slope, and beta 0 is nothing but the intercept. Yesterday, there was a question on that regression is also applicable. I forgot the name of the person. Is it
Kamal.
Alok or
Kamal.
Kamal? So sorry, Kamal. How are you doing, Kamal, this morning?
I'm fine, thank you.
Okay, so Kamal, yes, and now we are moving in that direction where we are actually going to use regression. Okay, so we are going to say that because there is trend in the data, and by trend we always mean not just I mean, obviously the increase decrease matters, but with time it should progress. If there is trend, you will see a term like this. A term like this will always be there if there is trend, because if there is trend, it has to be impacted by time. So there should be a term with in relation to t. Always keep in mind. Therefore, Holt's exponential smoothing uses two smoothing constants denoted by alpha and gamma. What is alpha? We know that alpha is the basic level smoothing constant. That gamma is nothing but the growth smoothing constant. There are two estimates, LT minus 1 and BT minus 1. So LT minus 1 is nothing but the estimate of the level of the time series at the period T minus 1, right? This is basically the permanent component. You know, that like, even if time did not progress, that's going to be the level. So if you see in the last methodology, after it is finished, it is finished. I mean, after the exponential, simple exponential smoothing is done, it's done. So it just goes, it doesn't carry on any further because it is not dependent on time. But in case BT minus 1, that is the estimate of growth rate and of the time series in the last period. And this is the trend component. So this is what will vary, keep on varying over time. And we'll see the details over here. How is the level estimate calculated? So if you look at the formula, till this part, it was the simple exponential smoothing formula, right? So let's just expand on this, right? So what do we get? Yt plus 1 minus alpha Lt minus 1, and then plus 1 minus alpha Pt minus 1. So this is the additional term that's coming in this relationship. Okay, now what about the trend estimate? So we will say that as time progresses, there is trend, right? The growth rate will keep on moving. So what we say is that it's gamma, which is nothing but the trend smoothing constant of LT minus the last period. So what is the level now? Subtract from the level last period plus 1 minus gamma BT minus 1. So if you see, in this format, it's always, this was the level estimate in simple exponential smoothing. Okay.
Yes.
Right. In this is the level, level estimate. Now in case of any kind of estimate, we'll see this is the common form. Okay. So like you have this constant, then you have the, then basically is the data given to you. So in case of growth, the data point is directly not given. What is given to you is YT, right? So you have YT, you have figured out the estimate of this time, this period estimate and the last period estimate. So for growth, the data point becomes the difference in the levels. The difference in levels becomes the data point. So the smoothing constant multiplied by the data point, 1 minus smoothing constant, the last period the last period estimate. So that's the generic form for all the smoothing, exponential smoothing equations that you will find. So in this case, for the growth, what is the data point? This is the data point, because you see this is the growth, this is the delta, right? This is
Yeah.
the basic delta. So you have the constant data point plus 1 minus constant multiplied by last period estimate all the time. So if you see over here also, where are we? Okay, over here also constant data point plus 1 minus constant multiplied by the last period level. Okay. Now point forecast made at time capital T for yt plus p. So if I say I want to go one period ahead, so I will say, okay, the period forecast, this is the LT, this is where I am, plus P times, if I'm going ahead for P number of periods, I would say number of periods multiplied by the growth estimate. So the level estimate plus the number of period you're trying to move ahead multiplied by the growth estimate. Once you do that, you're going to be able to come up with a point forecast, and we'll see that in the example. Now, the interesting part is that the calculation for SSE, is perfectly okay. It doesn't really change. MSE is okay. Now, MSE has T minus 2. Why do we have T minus 2 in this case? I explained why we had T minus 1 yesterday. My question to all of you is, why T minus 2 today? Why can't we have T minus 1?
As per here, for second step for YT plus P.
For this step?
Yes, for that.
No, that is not the right answer. No problem. Anybody wants to take an attempt? Like, why do we have T minus 2 here?
Is it because we are trying to find out two estimate? One is label, one is train.
Absolutely. Two estimates. One is the, it's the level, right? One is the level, and then the other one is trend. So what happened because of estimating these two? We lost 2 degrees of freedom. Okay. All right, guys.
Can you please explain the degree of freedom like you said, like it's number of covariance, variance is right. So what
No, it's not about, no, it's not, don't think of degrees of freedom in terms of variance covariance. Just keep in mind that, okay, I had to tell you what a statistic is, right? I don't know where to write. See, nothing, here's a simple thing. Always keep in mind that if you're using a sample, okay, and you're creating a function of sample values, it's called a statistic. Okay. Now, in terms of when we study statistical inference, these are two terms that are important. What is a statistic and what is a parameter? Okay, so parameter is basically connected with the population. If you're using a sample of a population and then building a function out of it, for example, if you see this one, right, it's always a sample. We are using half the observations anyway, and we are saying that essentially it's really the this statistic, this is basically a function of the sample values yt minus 1. Any, you can have any different other sample values also, or different other statistics also. Like, for example, this is a statistic, this is a population statistic, right? But if you want to do it sample statistic, you're going to say x minus x bar by small s bar. So this becomes a sample statistic. Okay, so a statistic is a function of sample values. what is happening here is when I create this, right, if I have estimated quantities in the sample, that those are not independent anymore because those are like, already estimated. So we will have to take away those many from degrees of freedom. If say this statistic is based on a sample of 100 observations, then each and every observation could have independently contributed to the entire value of the statistic. But the problem is that it does not. You already estimated 2 of them, so only 98 values are left as independent values. 2 values won't be able to. So you've lost 2 degrees of freedom. So over here in our time series, we have, I don't know, this is a theoretical section. So imagine that you have 24 data points, right? So 24 data points, if all of them could have been contributing to the calculation of MC, but they can't because 2 of them are already estimated. So 2 of them are estimated, therefore 2 needs to go away, and then it will be 22. Did that help? Always remember that we lose degrees of freedom. So that's why the number of estimated quantities will be subtracted in the denominator. Let's take an example where we're looking at weekly sales of LED. Let's call it LED bulbs for our discussion sake. So if it's that, then what's going on, right? So this is a weekly sales. So we have, what do we have? I think we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 12, 13. So 13 multiplied by 4. So it's 52 weeks given over here. And then we plotted the data. So it looks like, here's what it looks like. There is a trend here. So and it is changing because if you see, there's a very slow growth happening here. And then it is actually moving a little bit faster up here. So it is changing over time. And then there is some trend in the data. So that's why we will use double exponential smoothing in this case. And this is where, guys, Kamal, this is where we'll bring we'll start to bring in the regression aspect.
Yes.
Okay. So is this regression output something you guys, all of you know? Can you generate this output yourself? Not in Python. This is not in Python. This output is created in Excel using something called data
analysis. Can you please show once?
Sure, I will definitely show. No worries. So you guys want to see how to use data analysis to back, right?
Yes, in terms of regression.
Yeah, we will do that hands-on. Okay. Fine, that will be covered in the Excel section. No worries. Let's just quickly go through this. So what do we have here? We have taken half the number of observations. So we've taken 26 observations. Now we've fitted a regression line. What do we have? We have 52 weekly sales, right? So if I say this is 1, this is 2, this is 3, these are my weeks. So all the way up to 26 I've taken, and I've taken corresponding data points. So this is now my X. Now these data points are my Y. Okay, so I have fitted this equation. The equation right now is this. This is my equation. So you can see the R square value is not that great, but then we've got to, we have to sort of live with this R square value for now, but we are mostly concerned about this. So what is my equation? My equation is 202.62 minus 0.368 t. That is pretty much my equation because that's my slope. Time is my independent variable. This is my coefficient. So you can see this is the coefficient, this is the time. And then you have intercept, which is 202. Okay, now let's see how do we utilize this. Now, what do we know from L0, B0 perspective? That L0, L0 is this one, and then B0 is this one. 0.368 is B0 and L0 is 202.62. Okay, so we have this equation coming up. Calculate a point forecast of Y1 from time t equal to 0. So how do we go about it? we know that at time t equal to 0, and just one step ahead, if we go, we will have to say lt plus pbt. P becomes 1, so it becomes lt plus bt. In this case, lt and t is equal to 0. So we say L0 plus B0, because that's, we are substituting t by 0 here. We know from the equation there that L0 is nothing but 202.62, and then B is negative 0.36. So if you bring these two values together, you get 202.2564. So this is my the initial forecast. Then in step 3, we update the estimates of LT and BT by using the constants. So we are using alpha equal to 0.02 here and gamma equal to 0.01. So when we substitute this, it becomes alpha times the value, the earlier value, which is given here. This is the value. You will see this come here. Just a moment. Yeah, this is the first value, plus 1 minus alpha L0 plus beta 0. So you have seen this relationship. I will write it down over there again, so that we are all good. Just one moment. So alpha this one is the relationship, and this, yeah. So alpha yt is nothing but alpha in the current form is this 1 minus alpha 0.8 plus L0 plus B0. So we have to get L0 plus B0 because your time series starts from 1. So you have to at least go one step back. Otherwise, you'll not have T minus 1 and BT minus 1. Does this make sense, guys? Why do we have to do L0, B0? Because you won't have T minus 1 satisfied. So you have to start one step back. So when you bring this together, this comes out to be 203.0041. So the forecast against 206 is going to be 203. And similarly, in the I'm sorry, this is the level. This is just the level, not the forecast yet. Then we come to the growth part. Now the growth estimate is going to be again gamma times L1 by L. So we know that the growth beta t is equal to gamma times LT minus LT minus 1 plus 1 minus gamma BT minus 1. So what do we have here? L1 minus L0. We already know L1 is 203. It's calculated here. So we put that here, and L0 is something we substitute here. So this term can be computed. 1 minus gamma is 0.9 multiplied by beta 0, which is 0.3682. So this term can also be computed. We get a total result of 0.2933. Now, this is again LT plus P BT, right? From this relationship, we know that 203.0041 plus 1 period ahead, beta t, which is coming out to be 0.2933. So the period, the forecast made last period is equal to coming out to be 2.202.7118. This is the spreadsheet. So we started with alpha equal to 0.2, gamma 0.1. This is the initial level of estimate, initial growth, the growth rate also. This is coming from the equation. Then what we do is we basically update this one basis what we saw here. So 203.0051 is the L1 update. The L2, the beta 2 update is, beta 1 update from beta, because beta 0 is just from the equation, right? Half of the values. Beta 1 is updated by the relationship, and we know it's 0.2933. Therefore, forecast made last period, just a period ahead, just a period ahead from the last period. So it's going to be 203.0051. 1 second. Minus 29.33 equal to 202.2564. Then, of course, you have the error and the squared error. Okay, so this is Now, how do we move beyond 52? Okay, so how do we move beyond 52 and actually forecast the future? So when you are at 52, these values, they don't change, but what changes is the value of P. So if you are, say, if you want to, go T plus P, so you know that you're at 52, so 53 would be P equal to 1. So one period, 1 week, 1 week into the next year. So it's L2 plus 552, B52. So it comes out to be 320. And say it's 3 weeks, 2 weeks into the next year. So in 2 weeks, what will happen? So it depends on the factor. So at the moment this is how where it changes. And you can see these values are being this is where it is getting extrapolated. So in the 3 period ahead sales forecast for period 55 is this. 1 period ahead sales forecast for 55 is this. Okay, so now if we observe that when we move ahead, the levels don't make sense, we can either find a new alpha and so that we minimize the SSE for all the periods, or we can simply revise the estimate for the level and growth rate and recalculate the forecast by saying alpha 50 by, you can just continue to apply the formula and update the growth rate. If you continue to update the growth rate, that is one way to do it, or you can find out a new set of alpha for you.
Haritha, one question here. Suppose you say like next period means it's like a next week, right? So week equals calculation, right?
This is a weekly data. So next period will be week. Every data point is a period.
Correct. Yeah. And one more thing is the alpha and beta, whatever you're using, the intercept and all those things, that is a learnable parameter, right? That there is a learning happening, or
no,
that is randomly that?
Not random. I would say rule of thumb.
Okay.
There is no algorithmic learning there.
Okay.
I mean, you can't estimate alpha and beta. I see where you're coming from. No, you can't estimate alpha and gamma. That you can't. I don't think so. That's a bit of a thing, that there is no learning. But you can start with 0.1, try and make it 0.2, 0.3, and so on.
Okay, it's just like assumption we have to do. Like it's just hit and trials. There is no.
So trial and error, but yeah, but typically most of it will lie between 0.1 and 0.4 only. 3-4 cases. That's it.
What about beta values?
There are no beta, though, of course, you're coming right from the equation. The gamma, you mean to say, right? The growth constant, the growth, same thing. So any smoothing constant, there is no estimation actually. So you can't estimate, but just try between 0.1 to 0.4, it should be fine. But on this slide, the most important point is that when we try to forecast, right, you might want to just keep an eye on this parameter. Okay, this is the SSE, and this is the RMSE actually. This is the RMSE. So if you're here and say you have now calculated all the way up to week 72, you've done that. Now when you do that, up to week 72, you take all of the data and calculate your RMSE. If the RMSE increases from 27, that means you are, it is probably not that great. So what you want to do is make sure that either you try to opt for a different kind of alpha and minimize it. That is one option. The other option is to that you can keep on revising the estimate of level and growth and recalculate the forecast as explained here. So you already know the alpha constant that you have taken. You don't have to change alpha, but just use the same alpha to kind of progress. Because once you hit the last data point, typically we don't update the level and the growth. But if you think your errors are increasing, if you want, you can update the level update the growth using the relationship that you already know, and then that can help you.
But Aditya, isn't it learning? We based on the error, we try to reduce or try to increase.
You can call it, yeah, you can call it learning, but not algorithmic learning. It's just that it's the analyst's trial and error kind of learning.
Okay.
Okay, so you can't. I mean, or if you want to, like, I think, yeah, if you write a very custom program to get this done for you, then maybe you can automate it to some extent. That is something I haven't explored. Okay, so guys, questions, anyone? Questions, people? Nope. Okay. So let's just, I think what we'll do is we'll cover the next technique, and then we go to Excel and use the balance of the time to sort of actually, go through the Excel. Okay. So in Holt-Winters method, we will discuss multiplicative Holt-Winters method only. That's pretty much the most of the time we're going to do. So in this case, along with trend, we will have seasonality also. So the basic equation for us at the time when we describe the the time series model is gonna be beta 0 plus beta 1t. This is something we saw in the earlier method also. We started with this, guys, this simple equation, simple exponential smoothing. Then we moved to this, which is beta 1t. But we'll now have multiplied by seasonal factor, multiplicative model, and then the irregular component. So if you look at this relationship, this is the same thing which we spoke about earlier, where a time series can have a multiplicative component. There is no cyclicity in this model. So it's the trend multiplied by seasonality multiplied by irregularity. So the trend is given by beta 0 plus beta 1t. Clear? Any questions so far?
The one question is, like, how to know that which method to apply? First is that, but how to know that there is a, in the data point, there is a train and seasonality both, like in the, when you try to plot it, and like, can we find out we have train and seasonality?
Yeah, so you can. So by if the starting point for time series analysis is to plot the data. So when you do that, it will be very clear that how to sort of figure it out. I'll show you. I mean, in Excel it is there. So do you guys, how would you prefer that we get into the next method, or do we go back and actually see what's in the Excel and then come back? Or do you want to like get through theory and then you move to the Excel? What would you guys prefer?
First to show practically in Excel.
In
then
Excel?
we'll move for theory. Yes.
Okay, fine, cool, no problem. Okay, so we have a data set which is beer production. This is every month's beer production, and this is probably in million gallons. So now the data given to us is from 1956 January to 1995 month of August. Okay. Now this data, it's again, you can see the values in hundreds. It's probably going down a little bit, but it's in hundreds in the recent years. But it used to be in the double digits earlier. It really shot up in the 80s. If you just eyeball it, right, a little bit, so you can see that. But eyeballing doesn't help. So what you do as a first step is you just plot the whole thing. So once you plot it, you can see that there are like all these fluctuations. There are too many of these fluctuations, extreme fluctuations. But you know that there is no long-term cyclicity, so that is absent. You want to investigate for seasonality because you can see these fluctuations happening pretty regularly. Can you guys see the peaks? These peaks, they are happening so regularly. And also the falls. Can you guys see that? Okay. Now, how do I define whether it's a quarterly season or a weekly, a monthly season or whatnot, or if it's a half yearly season? I'm not sure, but it looks like, that if I am able to plot, so this is definitely seasonal because it's happening in regular intervals. So if I can plot 3-4 seasons together, then hopefully I should get some sense. So what I have done is I've plotted 2 seasons together, basically 1956 to the whole year of 1956 and the entire year of 1957. We can go one more year and let's see what happens if we plot 1958 as well. Okay. Now, when we say there is seasonality, we essentially mean that there is a peak and trough at regular intervals. That's what we are, that's what we are actually trying to say. Peak and trough at regular intervals. Okay. Now, in this case, we do find that interval to be this is the interval. This is where it's falling, and then again within this interval it is increasing. Again within this interval, it falls, and then again within this interval it increases, and it carries on. Does that help? Does that make sense, guys? Can you visualize what is happening? Let me know if this is making sense. Hello?
Yes.
Okay. So you can visualize what is happening, right? So at this point, till this, in this duration, it fell. In this duration, it increased. Again, in this duration, it fell. So there is a clear pattern here emerging where I can see peak and trough happening at regular intervals. So what is that interval? The interval in this case is 6 months. So every 6 months it falls, every 6 months it goes up. So therefore, I can conclude that a seasonality pattern exists every 6 months. So a season lasts for 6 months. So every month is a period in this data. So I would say 6 periods make one season. Good. Clear?
Arithra, can you try quarterly?
Well, I don't have to try, but every quarter it doesn't happen. So you see, where does a quarter lie, right? Okay, let's just plot it. So if you want to see quarterly, then every year will have 4 seasons. So I am good with just 1 year, right? So I need to remove all these, get rid of all these. Yeah, this is a quarterly. So it's a 12-month period. Now, if it was a quarterly season, you would have seen peaks and troughs at every quarter. Do you see that?
Yes, it's not there.
Not there, right? So there is one fall happening here, and there's one rise happening here. These are 2 points that are rise. But just by looking at 1 year, you can suspect that it is possible that it is a 6-month seasonality, but you cannot make a decision. So in order to make a decision, you have to plot more number of. So I tried checking for quarterly first. I mean, you should try checking for quarterly first by just plotting 1 year. Then if you don't find that, then you move one more year. Once you move one more year, you start to see some pattern that, okay, this is a fall here, very good. There's a increase here, again a fall, again an increase. So you can see a pattern begins to emerge. So that's when you start confirming your suspicion that it's most likely going to be a 6-month season. And when you plot 3 years, it becomes like a confirmation. Clear? Is it fine, guys?
Yes, yes, I agree.
Okay.
Yes.
Okay. Should I move on?
I have one question. Suppose here we are making a graph between X and Y, and whether is the quantity in can you just go in top? Yeah, quantity in production, monthly production. If we are want to do this in product wise, suppose 100 ml, 200 ml, and it's specific because that's the one business requirement. So for that, how we utilize this Excel sheet?
I don't think I follow the problem or the question. I couldn't follow the question. I'm sorry.
Okay, I will repeat. Suppose we are using here monthly beer production. But if we are calculating this beer production product wise, some specific ml, suppose for example of Budweiser and Corona, that's the 100 ml, 250, 100 ml, 500 ml. They want to make this for one. Suppose one product is a Budweiser. For that, they want to use the time series for all size 250 ml, 500 ml, and 100 ml. In that time, how will utilize this Excel sheet?
Utilize this Excel sheet will be useless because I'll tell you, this is what you will have to do. One time series. I'm just making it up. I don't know what are the MLs in Budweiser. I'm just making it up, okay? You will have 3 time series. You will have 3 time series. That's pretty much it. You will have to do the analysis 3 times. Every product becomes one time series. This is one, this is the other, this is the other. Okay. So that's how you, these are random numbers, obviously. Yeah, see, I took a rand between, these are random numbers. So these are just white noise. I mean, you don't really see any trend. It's not, I couldn't make a time series right now, but I'm trying to explain to you that if you want to do it for different products, treat it like a different.
So it will give only the single graph for all 3 time series, or we can make a
no, you don't understand. You're not able to follow what I'm trying to say. Every product, every unit will give rise to a separate time series. You have to do a separate analysis for each of them. One graph for one Budweiser, one volume.
Okay.
One graph for one Budweiser, one quantity.
Okay. Thank you.
Okay.
Yeah.
Got it?
Yeah.
Right. Okay. So monthly. This was monthly beer production. See, these are random values, and this should tell you something. See, there can't be any trend. See, there is absolutely no trend. Nothing to do. Like this is completely white noise, unmodelable. That's why it's random. Okay. Anyway, we'll discuss randomness later. But then, okay, seems to be an issue because the. Okay, so do we have any questions on seasonality and how did we get seasonality? How do we know there is seasonality in the data? What did we do to figure out how much seasonality exists? Any questions?
No question.
No question. Okay. Next is what we learned in exponential smoothing. Over here, we know that we are going to study we're basically going to use half of the observations to take the average of, and calculate the level, right? So what we've done is taken the level estimate with just the half. So 26 observations are taken into account. I think 26 weeks of data. So how many data points do we have in all? We have 476. So that is 238, 238, I think. Yeah, so this is incorrect. It should be 238. 238. Okay, we have the level estimate. Now we'll update the level estimate by the smoothing constant multiplied by the previous. So how do we do it? Here's what we do it. We've got the smoothing constant. This becomes a, this, it doesn't move, right, for every cell to cell. So this is in your this is fixed as a cell. So 6C2 multiplied by C6 is nothing but your the YT value. So you have L0, but you have YT, Y1 actually. So that's the Y1 value plus 1 minus alpha multiplied by the previous level estimate, which is 113.83. Now this is just an estimate based on the initial half of the observation. So you can essentially think of it as a starting point. Now this is going to be the starting point for all the subsequent exponential smoothing. Once you get the level estimate updated, so you're pretty much it, because that is that's what you have to sort of actually update from the smoothing equation, and then the forecast made last period is given by what you have here. So for when I say L0, I mean that's the forecast that I made in when time equal t equal to 0. So this is where I start from and I carry on. So my last value is going to be 153 versus 142. Over here, I get the error in this column, and then it is a sum of square errors. So once you do that, you are able to see the what the SSE value is. So you just sum it up here, okay, and then you divide this by n minus 1. N in this case is 476. So MSE comes over here, and then you take a square root of that to get the RMSE. So alpha is taken as 0.12. So I have just kept on iterating on this. So you can see if you just keep on changing alpha, what is the impact on the RMSE value. So if you say keep alpha equal to 1, see the impact on the graph. Okay, our alpha equal to 1 almost becomes an identical graph, because the forecasted values and the actual values almost overlap. But if you keep alpha equal to 0.1, you can see the line has become much more smooth, and you have been able to uncover what lies beneath. So all the noise that you find, all the fluctuations that are here, all the noise that are there, this is going not bothering this line anymore, because it's a smoothened line. It is starting from a higher point, because 113, this is the point, and this is your 93.2. So it's starting from a higher point, but then it quickly follows through the center of the line and it carries on. So you can see that this is a very smooth line, curve. In order to see how good a fit it is, you can do a right click on this dark blue line. This is very helpful, guys. It, very quick and give us a good sense. So it's right click on the dark blue line and just do add a trend line. When you do that, you're going to get a lot of options, but try to incorporate, say, linear regression. Okay, and just say that I want to display the equation r square value on the chart, or the equation, both. Now just drag it up here. Yeah, you can see how good a fit this is. So basically it's, if you were to do a if you now use the blue line and say you just do this, right, and you use the time as a driver, time as an independent variable, and build a linear regression line, you will get a good R square, 73%. So that's a pretty good R square. So simple linear exponential smoothing seems to not, it's not that bad within this data, although we have not taken seasonality, etc. into account. Okay, now we go to double exponential smoothing. In double exponential smoothing, so in case of double exponential smoothing, what's happening here is that, is there a question? Okay, no. So we have first of all two constants, 0.1, don't mind the values just now. Let's go through the formula. Now level estimate and growth estimate, they have to now come from, they have to be, they have to come from regression. Because why do they have to come from regression? Because we are assuming there is a trend in the data. Now, if there is a trend in the data, we know that the trend has to be yt equal to beta 0 plus beta 1t, right? So this one has to be estimated. This also has to be estimated. It can't be a simple average. So therefore we will adopt the regression technique and then sort it out. So let me just clean up some tables. So that it's decluttered. Okay. Now, don't mind these values. So what we do is we go to data. I already have this pack called data analysis tool pack. Would you guys like to see how to install this tool pack? Because it's pretty cool. When you click on this tool pack, you will see that Excel can operate, actually do a lot of things for you. It can actually give you, test of variances, ANOVA, major descriptive statistics analysis. You can do this ranking and percentile variations. Hypothesis testing becomes very simple. You're able to do regression also. You're able to do moving average. You are able to do exponential smoothing as a package itself. You don't even have to do it by formula, but I'm trying to teach you by formula. So you can, so that you're able to understand how it works. But yeah, this is pretty cool. Would you like me to go through the installation of this?
Yeah.
Okay, so you go to file, get rid of this, go to file, then you come to options. Okay, when you come to options, you'll find all of these various things on the left hand side, but then when you scroll below, you will find something called add-ins. Here is where you have to go, add it, and when you click on OK, not sure what happened. Yeah, when you just double click on add-ins, so you can see all of these options, right? So it's a solver add-in. Solver is for optimization. Then power pivots are obviously there and other things. But I have found this analysis tool pack to be a great add-in. So I have chosen that. It's already active. That's why it's showing here. Otherwise, inactive, it would have been showing in the inactive list. Because I have selected it, it is now showing as one of those active application add-ins. So all you got to do is just press OK, and that gets auto installed. It starts showing up under data. So now when you click on data, when you come back or restart your Excel, you go to data, and then you can see this option, right? Data analysis. So how do we use this? It seems to do a lot. It has a lot of options here where we can choose to do different things, but how do we actually use it? So it's very simple. It's a menu driven thing. So you just click on OK. It asks for two basic inputs. What is the Y range and what is the X range? Y, of course, as you know, is the dependent variable. X is the independent variable in this situation. So what I'm going to do is I'm going to say that let this monthly beer production be Y. And we know we've got to go to use only half the observations. So I know the number, so I can just type it, 238. Now I go to X. When I go to X, okay, a quick audio check. I just switched on my fan. Is it still okay, or are you getting some disturbance in the background?
It's fine.
It's fine?
It's fine.
Fine, okay. Because I have to ask you this because, whenever I have these conference calls in my office, there is a lot of disturbance because of the fan. So I just switch it off and have my calls. Okay, so I have created a column called time period. Why? Because it is essentially you can think of it like it's nothing but the period. So against every period there will be a value given. So I've just for convenience sake, I have that column here. So I'm just going to go ahead and use this column. And I also know that, yeah, it has to go to the row number 238. So now both of these are here. These are all, when you actually do a proper multiple regression or linear regression, you can actually do many things. For example, line plots, residual plots. They're interesting for our purpose. They're not required. So I'm not showing that. So I'm not clicking on them. Normal probability plots, these are also very interesting. So if we have time, sometime maybe I can either show you how to sort of use these, but yeah, they're definitely informative. So let's click on OK. I just want to get rid of the grid lines. So I click on view, got rid of grid lines, expanded my columns. Now, okay, here we are. Very well. We have an adjusted R square of 67% with 233 observations. I don't understand. So why do we have 233 observations? Didn't we choose to use 238? Oh, I know why. Probably because of the row number. Just bear with me a second, please. Oh yeah. So you see, I manually typed 238. What happened was it came to row number 238, but that does not correspond to the 238th observation. So the 238 data point corresponds to row number 243. So we've got to update that. Did you guys follow what happened? I made that mistake. So yes. Yeah, you followed. Now the count is 238 and it corresponds to 238th count corresponds to, I think, row number 245 or 243. Okay, it's good. Now go back there, go to regression. Oops, my bad. I'll get rid of this output because we're not going to be able to use this output. Let's call it level estimation. Double explanation. Okay. So what do we see? Okay, this is the equation that's coming up. Now, this is the growth rate and this is my level estimate. So 72.94 and 0.34. So if I take these two values and come back here and say I go here in my template, then I do transpose and I put these values there. I then basically make sure that, yeah, my level estimate is nothing but my intercept. My growth estimate, these are now estimated from the model. So beta values are here. I already know what my gamma values are. I know my gamma value, so I can just try to put some different gamma values. Yeah. Okay. Yeah. Now the level is increasing by this relationship. So we have alpha multiplied by yt plus 1 minus alpha bracket open L0 plus B0 in case, I mean, previous level of previous level estimate plus previous growth estimate. Why? Because, you know, the trend itself is composed of both the level and the growth estimate. In the next step, we will update both. I mean, obviously level got updated, but growth also needs to be updated. So we know that from the earlier relationship, right? It will be gamma over here, and then it will be multiplied by the difference of level. So L2 minus L1 plus 1 minus gamma multiplied by the previous estimate. So like I told you, the basic smoothing constant formula structure is that you have the smoothing constant multiplied by the data point plus 1 minus the smoothing constant multiplied by the previous estimated level. So in case of slope or growth estimate, the previous estimated level is in E5, which is 0.35. That's why it's coming here. Then you have D6 minus D5, nothing but L1 minus L0. So this is the difference of level. From a growth point of view, this is the data point given. So you have the constant multiplied by the data point plus 1 minus constant multiplied by the previous estimate. So in this case, we have the growth estimate up to 0.75. Now, once we get this, we've got to simply add it. I think add it. Hang on. Make sure that you are good. Yeah, this is positive. So we've got to add it. We just have to add it. Yeah, right. These two is the last period estimate and the growth estimate comes together. This becomes my forecast made in the last period. Then when I compare the error, I will be comparing between 93.2, 73.9 and so on. So the rest of it is quite simple to all of you now because it's squared error and then summing up of squared error. MSE has to be carefully, MSE is incorrect. MSE is going to be this one, T minus 2, and then you have root mean square error. Okay, so we've got 19.81 in this situation. What if I try to have a better smoothing constant or higher smoothing constant? I get a slightly better MSE. I get a slightly better MSE. If I try to improve it slightly, it becomes even slightly better. No. So if I increase alpha, it becomes 0.76, 19.76. So if I bring it down, in fact, say I bring it down to 0.15, it comes actually lower, then it becomes 0.62. What if it becomes a standard value? 0.52, even better. So now why don't I just try this? I think we can probably settle down here. Let's see what the line looks like. This is how the line looks like. And if we say like we did earlier, let's just quickly add a trend line to see what are we kind of doing. It improved slightly from 73 to 74. So in this case, it was what, 73.4. It actually improved. I think it can be further improved. Now there's a note I have here. Now when we there was a question that why does the slope and R square decrease if we consider all of the data, right? When we consider all of the data and do a regression, it actually decreases because it changes direction multiple times in the given time frame. When we choose only 230 observations, actually it should when we choose only 238 observations, we are deliberately choosing a time frame where slope has not changed the direction. Therefore, the magnitude of the slope also increases. So if you take if you do the regression, you want to calculate, say, this one based on the entire data, then it won't be that accurate because you're choosing a time, you're choosing the entire time range, and the direction of the graph has changed multiple times. It has decreased here and then it has increased again. So there is no net slope will actually reduce. So slope is always between y2 minus y1 divided by x2 minus x1, right? So the net slope actually will decrease if you take the entire range. So let's try see if we can improve this a little bit more. The R square value doesn't really, slightly actually. Yeah, this is only slight improvement. So what if it becomes a 0.5? Yeah, it looks like it becomes, yeah, we can probably stop here. It's perfectly okay. We don't go beyond this number, 0.5 typically we don't, as a rule of thumb. So if it is becoming the best at 0.5, then let it be. Okay, so now we've done till this point. Now what we will do is when we go to the Holt winters, we'll keep these two constant, and then we try to see when we bring in the seasonality, does it improve matters or not? No, I will have to, just 1 second, guys. It actually became worse. Yep. I guess our optimal point lies somewhere here. 0.35. That's where our optimal point lies. After that, the R square starts to reduce. So let's keep it there. So we are now going to close the double exponential smoothing activity because we've now hit the point where we are fine with the R square. it was a trial and error, but we know that this is the best that we can achieve with the double exponential smoothing as of now. So any questions, guys, till this point, because we'll have to go back to the theory. We will discuss the whole winters and then come back here again.
Aritra, I have one question only.
Yeah.
Like, I want to see the difference when there is just seasonality on trains, and when there is a seasonality, there is no trains. So how it will look like the graph, and is there an example you have?
If there is seasonality and no trend, that is it possible to have seasonality without trend? I'm thinking, is it possible to have seasonality without trend? It is possible, I guess. But in that case, yeah, you could apply simple exponential smoothing there, or you can apply seasonally adjusted simple exponential smoothing, but you're not going to, like we have it here. So there's a pivot, and this is analysis that you've done to do the seasonal estimation. So we can do that over here, except that the estimate will not come from regression model. It will come from just the one level, the average value. So I guess I don't have an example right away, but
I just want to see that, like how it does look like, because we have to analyze, right? From the data point, you have to analyze that. Okay, we have the trains, but we don't have the trains. Like that, I want to see the things. Do not? If you have example, or you can just show us that things, then it is also better.
It is. It's difficult to come up with specific examples online with data sets like that, where you have trend but you don't, where you have seasonality but you do not have trend. So what if I don't have an example? I'm not able to give you that example right now, because I mean there's no data set where that kind of behavior is being shown. But you can probably come back here and look at the R-square value. See, it's not that bad a fit. It means that the seasonal aspects that are there are not that strong. It is there for sure, because we've seen it in the visualization. We can see it, but it's not that strong. What I mean is, that when it's falling from 100 to, where is it falling to? I think it's coming down here. But if it was a deep seasonality, something like this, right? This is actually a much deeper seasonality. So even in this data, you can see that there is obviously some seasonality for sure, but it's not very strong in that sense. So you can get a sense of how it would look like from this data also, because exponential smoothing is not doing that bad a job. Simple exponential smoothing would have been really bad if there was very strong seasonality. But as when we do the seasonal analysis, you can see that the seasonal aspect is, seasonal indices are not that strong. So let me take an example here. But that is for, I mean, you will have to wait till I actually cover the whole winters. But with regards to double exponential smoothing, is the concept clear? Do you think this is doable for you guys in Excel? I mean, at least from an Excel perspective, is the comfort level there? Any questions on double exponential smoothing? No? Okay. But Kamal, you can try to visualize this data itself, because the R-square value is not that bad, meaning that there is almost, I mean, there is seasonality for sure, but pretty weak, as if it's almost that the indices are not going to be that much strong. So that way, this is an example of how it looks like. Okay. But yeah, is there a specific so is there a specific question related to the seasonality or say double exponential smoothing? So allow me a moment, guys. I'm getting a call. Just 2 minutes, please. Thank you. Hi, hello. Thanks,
Yeah.
thanks for waiting for me. I mean, I actually got a call from my brother. Because of lockdown, he was in hometown for 5 months. He's coming back to Gurgaon. His office laptop actually is not working, and they're not going to deliver back in hometown, so he has to actually travel all the way back here. So yeah, he was just telling me that he's left home. So after a long time, he got to spend 5 months at home, which is very rare, right? Um,
Yes.
5 months at home, who gets to do that? Anyway, yeah, coming back to this, I guess, so come on, I think, this probably should give you a glimpse of how it might look like. But more than what it looks like, I just want to make sure that is the methodology more or less clear to people, because you will have to play around with this Excel sheet. This is a good template for you guys to plug in numbers and see how the numbers move. You can go online, pick your data, pick any data set of your choice, bring it here, and change the graphs to see how the data kind of looks like, and then do a thorough analysis on Excel. So this is the template I've designed for all of you, and it will be there on the
In
portal.
this sheet, can you explain what is the adjusted R square?
Adjusted R square is the typical
Last slide.
the adjusted R
Yes.
square. Yeah, so adjusted R square is the model quality metric from OLS or linear regression. So linear regression model quality actually. So R square essentially is the percentage of variance
Yes.
explained by the model. And there is an adjustment that happens on the R square. I think I'm not able to recall on top of my head. Would you mind if I get back to you later on?
Yeah. Yeah.
That okay?
Yes.
Okay. Okay, guys. So I take it that most of you are now at least somewhat more familiar with how double exponential smoothing is done. The main difference lies in the fact that because we are recognizing that we are acknowledging rather that there is a time dependent trend in the data. Therefore, we are choosing to do a regression to find out the slope. Once we find the slope, it becomes important to update it at the next level by the slope smoothing constant, and then the level is coming from the intercept part. So the only question we have not answered till now is that's the only question we haven't answered is that Orithro, we've seen all these seasonal movements. You haven't really done anything to address seasonality till now. That is the only problem that we haven't addressed. What we're going to do is that we're going to look into something called Holt-Winters methodology, and then go from there, really. Okay. So Holt-Winters is what we're getting into. This will address the question of seasonality. All right, so we are good so far. Shall we take? Do you guys want a 5-minute break? Is that okay?
Yes.
Everybody okay with that? All right. Okay. So 5 minutes or 10 minutes?
10
Let me know.
minutes.
10 minutes. Okay.
10
What is the
minutes.
time now? What is the time now? It's 10:40. So I'll be back at 10:50 sharp. Okay. So we'll
Yeah.
discuss it. So I'll pause my screen right here, and we will, one second, what is this? Yeah, we'll be pausing it here, and this is where we'll start from. Okay, I'll see you in 10 minutes then. Thank you. Hi guys. Shall we start? Hello? Hello?
Yeah, hi. Yes, please, you can.
Hi.
Yeah,
Sure. Okay, any question? May I know your name?
Megha this side.
Hi, Megha.
Yeah.
Megha, do you have any questions or anything, any doubts to discuss?
No, you can proceed.
Sure. Thank you,
Thank
Megha.
you.
All right. So we're going to talk about what we know, also known as multiplicative whole twin-terms method. Okay. So now over here, the difference between the earlier method and this one is that we are acknowledging the importance of a seasonal pattern in the data, and we will consider a multiplicative format for the model. So as I just described over this section, right? So in the multiplicative format, we have the trend component multiplied by the seasonal component multiplied by the irregular component. The trend is given by beta 0 plus beta 1 t. Therefore, it's beta 0 plus beta 1 t multiplied by S and t multiplied by IRT. IR is nothing but the irregular component. This method is appropriate when a time series has a linear trend with a multiplicative seasonal pattern for which the level beta 0 plus beta 1 t, growth rate beta 1, and seasonal pattern may be slowly changing over time. So at this point, I had the question coming from Kamal as to how to visualize the data, at which point we went to this Excel sheet and we saw how to visualize. Okay, so moving on. Now, estimate of the model will now have a seasonal component to it. Okay, so it will be alpha yt divided by SNT minus L. So SNT, I'll show you how to, we'll discuss how to calculate SNT minus L, but depending on the seasonal index, the number will be deseasonalized. The deseasonalized data point will be taken into account plus 1 minus alpha, LT minus 1, the level and the growth. So this part you have seen in double estimation. In this part, the deseasonalization of data is taking place by way of dividing it by the index. Estimate of the growth rate, again, the format is simple. So it's going to be the smoothing constant, the growth rate smoothing constant multiplied by the data point plus 1 minus smoothing constant multiplied by the previous estimate. So it's gamma LT minus 1 plus 1 minus gamma multiplied by BT minus 1, followed by estimate of the seasonal factor. So estimate of the seasonal factor is smoothing constant, the deseasonalized data point here plus 1 minus delta, which is the smoothing constant delta here. So 1 minus smoothing constant multiplied by the previous level. So you can also see over here also the basic nature of the equation continues to be the same. You have a smoothing constant here, you have the data point, previous data point here, plus 1 minus the smoothing constant multiplied by the previous estimate. Okay, so we're saying that alpha, gamma, and delta are smoothing constants between 0 and 1. Capital L is number of seasons in a year, and if it is a monthly season, then L will be taking the value equal to 12. If it's quarterly season, then L will take the value of 4. In our example in Excel, L will take the value equal to how many?
12.
Sorry?
It will be 12.
12. L is the number of seasons in the data. 6 months, right?
6, yeah, sorry, 6.
6. Are you sure it's 6? L is equal to 2. Why? Because from month 1 to month 6, one season. From month 7 to month 12 is the second season. So you have only 2 seasons a year in our example in Excel. So L equal to 2. Clear? How did we get L equal to 2 in the Excel sheet? In the
Yes.
monthly beer production? Okay. So Yeah, now we know that in general, if the, where you have trend, it will be LT plus PBT. But in case, because we also have to recognize that seasonal impact is there, we'll say LT plus PBT multiplied by the seasonal index of T plus P minus L. So T is going to be the point of time where you are right now and you're trying to focus ahead. The P is nothing but the number of, the periods that you're moving up ahead. And capital L is essentially the number of seasons, right? So the correct index will have to be multiplied in order to get the forecast 1 period, 2 period, as many number of periods ahead as required. Then I'm sure by now all of you know why we have 3 here, because we have estimated 3 quantities or 3 degrees of freedom, and therefore the denominator has moved from t minus 2 in the earlier methodology to t minus 3 in this methodology. And but the metric remains the same. It is the RMSE, or root mean square error, also abbreviated as RMSE value. Okay, so that's that's just the theoretical part. But what we will do is we will use a data for the sale of Sprite, and it's given to us in a quarterly fashion. So we have data available for 8 years, but for every quarter. So year 1, quarter 1, 72, year 2, quarter 2, 116, 136, 96, and so on, right? We will use this example to build a case for multiplicative Holt-Winters method. So when we plot it, like for all time series problems, we plotted the data. We can see that there is seasonality, and if I could just zoom a little less, I think it's probably yeah. Now it will be visible to all of you, I think. Yeah, at least you can see. So where am I? Yeah, so this peak happens in quarter 3, then it is followed by a peak in 7, and so on. So we will try to see if we are if there are quarterly indices that are there. So what are our observations? Our observations supporting Holt-Winters. Why does Holt-Winters make sense in this case? Because we will have to build a case step by step. So our observation is that there is a linear trend over the 8-year period. So let's go back and see. Yeah, there is some sort of upward trend for sure in the 8-year period. The magnitude of seasonal span increases as the level of time series increases. So that if you just look at the graph here, you'll see that the increase, so the slope here, right, the slope here looks a little bit, the slope is much flatter than the slope here. Can you see the seasonal impact? So the seasonal impact also is slowly changing over time. I mean, obviously there is because of seasonality you can expect a spike, but how much spike, how much growth, or how much additional spike I can expect because of seasonality, that how much question is also changing. The answer to that how much question is also changing over time. So as time progresses, looks like you can expect more, the impact of seasonality to be much more than what it used to be 8 years before. Now, because of this, we can say that the magnitude of seasonal span increases as the level of the time series increases. Multiplicative Holt-Winters method can be applied to forecast future sales in this case. So we have therefore concluded that because of these two observations, we are going to use Holt-Winters. Now let's proceed to actually doing it. Now initially the level of L0 B0 are obtained the exact same way, like by doing regression. So we have 8 years data given to us, so it will be 32 data points, out of which we have used 16 data points to create the output, because it's the intercept is 95. You can see it here. You can't see the beta zero value is sorry, the B0 value is 2.4706, nothing but the slope. This is the trend line that we come up with when we perform a simple linear regression on that data. We also have to estimate the seasonal factors Sn minus 3, minus 2, minus 1, Sn 0. So recall that we spoke earlier that we have to, the initial estimate is all about before time began, before your data even began, one period prior, right? Now we are talking about 4 seasons, one every quarter. So there has to be 4 indices prior to when the time started. So Sn 0 and then go back Sn minus 1, Sn minus 2 and Sn minus 3. And like we saw in the theory part, as we go deeper into the time series to keep forecasting the values, we will be updating the seasonal indices step by step. But we need an initial starting point. So, and we need 4 starting points for seasonal indices, because in this case we have 4 seasons to begin with. Make sense, guys? So now there's a lot of numbers here. I'll go through it one by one and try and explain to you in a step-by-step manner. Don't get intimidated by the content in the slide, because there has to be additional content here. So let's just go through it step by step. So now, what is step 2? The step 2 here is the initial seasonal factors we have to compute. So we compute YT, which are in sample observations for fitting the regression. In this example, T is going to be lying between 1 and 16, because we've taken 16 examples. Now, once we do that, from the regression equation itself, we get some forecasted values. We will call this Y1 cap, Y2 cap, all the way up to Y16 cap. What we do is we detrend the data by computing ST equal to YT cap. Now, from our moving average discussion yesterday, we saw this being done. So we saw that, if the seasonal relationship is nothing but your data divided by the moving average is going to give you seasonal component and then the random component. Do you guys remember that? So over there, my forecasting was being done by this. If I'm forecasting using the linear regression, then this doesn't matter. The methodology for getting the estimate doesn't matter. The estimate has to be in the denominator. So the estimate is now in the denominator, which is now coming from a regression model. So now let's figure out what will happen in the next step. In the next step, you will have an actual value from the time series data given to you. You will also have the estimate that will come from the regression. Over here, you will calculate for 16 values. You can actually calculate the values like this. Now, we will average the seasonal values for each of the L seasons. The L values are found by computing the average of the detrended values for the corresponding season. So for quarter 1, it is season 1. Season in the first quarter, it will be season 1. Then we will take the 5th one. Then we will take the 9th one and the 13th one. So we now have an average value of 0.7060, which is basically all of the seasons combined in that quarter. Okay, so every quarter you have a season. So every year there are 4 seasons, right? So I take the first season of the first year, and then the first season of the second year is nothing but S5. First season of the third year is nothing but S9, and so on, right? So it's like that. So 4 times, so that's how we will actually calculate. So we'll get 0.7062 for everything connected to the first season. Multiply the average values in such a way. So again, this is same calculation that we saw yesterday. We are going to sum it up, and once we sum it up, we will have to adjust it as per so that the values become equal to 1. This is just making sure that each of these values they add up to 1, because all of the seasonal factors, they need to be finally adding up to 1, because all seasons can occur only once, and therefore when you take every season together, from a probability standpoint, it becomes a sure event. So therefore it has to be, from an index point of view, it should reach the value 1. Now you have once you calculate these seasonal values, so Sn3 minus Sn minus 2, Sn minus 1, Sn 0. So these are my 4 initial estimates. How did I get Sn 0? Sn4 minus 4. Over here, it is 0.8886. And then for 1 period, which is again the same thing as 0.8886. Sn minus 1 can be also represented as Sn3 minus 4. So over here you can take SN3, which is 1.29. So these four indices are now created for before my time started. These are my four indices for my these are my four seasonal indices basically. Now let's come to the update part. So when we calculate the point forecast of y1 from time t equal to 0 using the initial values. So we have L0 plus B0. In this case, P is equal to 1. So we take L0 plus B0 multiplied by Sn1 minus 4, because Sn t plus P minus L. L is nothing but 4. T is the point you're trying to estimate. So 1 minus 4. So we say that we'll take the first value, Sn minus 3. So in this case, it's 95, because 95 is the data point given here. I'm sorry, 95 is this one, 95.25. B0 is again this one, 2.47, multiplied by the first seasonal value, which is 0.7062. So you get 0.69, right? Step 4 is we update. We update the three things, LT, BT, and SNT, using the relationship that we have. So it's a simple calculation here now. So we say that, okay, we will take alpha, we'll take the data point, in this case it's 72, divide that by SN1 minus 4, which is nothing but, in this case it is minus 3. So we basically take the first point and minus it, and also 1 minus alpha plus the couple of the level and the growth. So when you bring this all together, you get the new level to be 98. The new growth estimate is gamma multiplied by the difference of levels. So we do have that plus 1 minus gamma multiplied by the growth estimate. So in this case, it's going to be 0.1, 0.985, 95.2 plus 0.9 multiplied by 2.4. So we get 2.5553. Okay, so these are two updates that happened on the level and on the growth. In case of the seasonal update, the smoothing constant is multiplied by the value divided by the level that we already estimated. We've estimated 98.5, so we put that here. Then 1 minus constant level, which is 0.1, therefore it becomes 0.9, and we take the initial estimate, it's 0.702. So now we have three updated values. Once we have three updated values, we will use the new numbers 98.5 plus 2.4 and then SN2 minus 4, which is nothing but minus 2. So minus 2 is already pre-calculated here. We know minus 2 is coming from here. So we put that and we get this number. Okay. And this continues, right? This will be on. So I have a couple of other slides to just show you the calculation. But really speaking, this is where it all comes together. So you have 4 seasons before the data starts. You have the level and then you have the growth rate. Okay, you're updating the level, you're updating the growth rate, you're updating the seasonality, and you're bringing together the forecast in this column. Once you do that, you're then you get the chance of calculating you then move to the calculation of error and also the squared error leading up to RMSE. That is what we do. But then in terms of, yeah, sorry, let me take a pause here to see if there are any questions before we proceed.
So this calculation we have to do manually, or there will be any automation or something?
No, you don't have to do manually. In Excel, obviously it's formula driven, but in Python, there are packages to get it done for you.
Okay. Do you have any script? So we have to run that script, and after that we'll get whatever we are expecting the output.
I have a script. I will be in our next class, we will be discussing that script for sure.
Yeah, sure.
From 3 p.m. to 6 p.m. like we agreed, right? Next Saturday. We'll be doing that. But if you want to go through it beforehand, it is already available in the portal I shared the link for. It's there.
Okay, thank you.
Okay. Question, anyone?
seasonal factor, whatever we are calculating, right?
Mm-hmm.
So that is like, because we have 4 seasons, that's why you are calculating 4.
4, yeah. If you have 2, you'll be calculating 2. If you have 12, you'll be 12. Okay. Now, when it comes to moving ahead, so we will have to, you can use this relationship LT plus PBT multiplied by SNT plus P minus L. So if we had 32 data points, right? We want to move so one step ahead. We will just use this. So 33 minus 4 is SN minus 1. So we already know this. So we'll use this seasonal. This is how we'll keep on updating it. So 34 becomes L32 plus 2B32 and so on. All right. Pardon my voice. So let's have a look at the Excel implementation. It will be a lot more clear. Okay. So we know that we have to do two things, right? First thing is that we'll have to do a regression, and we've already done that. We've done that here, but let's just so that we give ourselves some practice, we'll just do it again. We click on data, go to analysis, click on this one, 43. This is what we are calling as Y. No, that is incorrect. This is going to be Y. $238 data points is what we need, right? So 238. Let's just make sure that we use 238 data points. Sorry. Yep, found it. Once we do that, we can just modify this to C column. Yep. Doesn't have the same number of rows. Oh, I see. Oh yeah, it starts from 7. My bad. Yeah. Oh, okay. Do we get the same observations, the same values? We should ideally get it 72.94, then 0.3488, right? Let's see. What did I use? Yeah, 72.94, 0.3488. This one is probably from an earlier exercise. I will delete it just so that we don't confuse ourselves. 72.94 and 0.3488. This is a consistent observation between this and this. So we can use this output to quickly, put our level estimate. So this is our level estimate and our growth estimate from the model. This is now done. We are left with calculating of these two. And as I was saying, the seasonal values come to be 0.92, 1.02. So you can see that 0.9 is almost 1. It's not very different from 0.92 is not very much lower from 1. So the impact of seasonality is the indices of seasonality are not that strong, but we will see how to calculate that. So the first thing we do is we go back to the deck. In the deck we saw that we have to calculate the YT, which will come from the regression model. So let's do that. First of all, what is the regression model? This is the regression model. So let's take this. So estimate from regression is nothing but it's It's a simple equation. So we're saying that it's coefficient Q2 that remains constant. This is the intercept plus the slope multiplied by the given data. So it's beta 0 plus beta 1t. This is fine. So we got the regression estimate. Once we get the regression estimate, we have to then calculate the the yt divided by regression estimate actually. So what we do here is so we get the D200 values, y divided by estimate. Are you guys able to follow? Hello, everybody. Are you able to follow?
Yes, yes.
Okay. No loss of data has happened. No, but then we, 1 second. We will only use half the values, right? So when we say half the value, we mean 244. So we'll have to go till 244. Sorry, 238. Row number 238. Okay, this is how much we'll have to use. We can get rid of this. And then let's see what is the next step. Next step is that we list out. So if it's because it's a half yearly season, so we'll have 2 seasons, right? So H1 and H2 in that sense. So what we have done here is that we've created, I created a formula. I've taken a substring A2 comma 2. And if that substring value, if the value is less than or equal to 6, I'm calling it H1, except other than that is H2. All right. So I have a pivot table here. What I'm going to do is arrange the data in this manner. So I have different years here. Okay. The various years are present here. And we also have the different elements or different seasonality here. So as you can see, we had the different data points. So if you can just see, there are 2 seasons and you have number of years, right? So, on the columns. So in case you are not able to relate, I have converted the data to look exactly like this data. The seasons on the rows, years on the column. Can you see that I've converted exactly like this in the pivot? Guys, if you're not able, can you please respond to that question? So all of you are able to see what I did, or hello? Anyway, so I think it's clear then in that case. Okay, so the data now looks exactly the way it is described there, where you have the seasons on the rows, different columns on the as years. Now what will happen is it will then become an exercise where we will have to take an average, like we described here, that we take the first season value from the first year, first season value from the second year, and so on, to get the average. So how do we do that? We take the values coming from this section of the pivot, just copy, go here, to hold winters. Just 1 second. Yeah, okay, we're good. Just paste it here. All right, just so that formatting remains constant. Oh, I'm just going to keep this here. Okay. The earlier values were not, it seems not that accurate, but then again 5.7 is close to 6, so we are saying that we have to average it across all the years. So just as I'm trying to explain with the deck and the Excel so that it becomes relatable. So you have, in this case, how many points did you have? You had 32 points. Why? You had 4 rows across 8 columns, 32 points. Now you're just going to concern yourself with the first 16. First 16, you will have, essentially, the data for just the 1/2 of the time frame given to you. So how much of it is given to us? Let's just quickly check. We are given time frame till 1995, but we have only used time frame till H2 of, so we haven't completed, if you just look at the problem here, the issue is we haven't completed 1975 totally. So we can probably extend that and complete 1975 totally, so that we know we are dealing with. So how many years are we dealing with? We've been given 1956. Sorry, not 1856 and 1995. So we have 39 years. So if I round off to 40, I get 20, or else mostly 19 years, right? So 19 years. So 1975 tells me that I have consumed exactly 19 years. And then just 1 second. Yeah, so 19 years is what I use, because you have to use half the time frame. So let's come back to the pivot table and quickly refresh this, because we hadn't used. Yeah, the numbers are going to get slightly updated up to 1974. No, we have to refresh the pivot table because it's not correct. We'll have. Are you able to follow what's happening? The earlier pivot table was not that correct. Actually, I'm actually doing it hands-on in this session. So we have to use 19 years. So the pivot table actually considered only 18. Perfect. Now H1, H2 comes here. My year goes here. And my detrended values come here. Perfect. I copy this and I paste it, because it has gone to 1975. I have one more extra column. Right. Now it becomes a simple exercise in which I have to take the average across the time frame. Now, if you go back to the PPT, you'll see that because there we had 4 seasons, right? So I'm taking the first season from each data point. Over here, we have 2 seasons. So I will take the average. Yeah. Okay. Yeah. I'll take the average across all the data points. So first season from the first year, first season from the second year, first season from the third year, and then average out this row. This is what I'm interested in. And this is what I'm interested in for the second year, because that's what is happening. The first season being taken from first year, first season taken from second year, first season from third year, and so on. That's how you get the complete average of the first year. Okay. Now, how do I adjust it? So let's just get rid of all these. Pictorial representations. Okay. So we get this. So it's 5.8 versus 6.2. Now it looks like, yeah, I probably hadn't done it correctly last time. Let's call this basic seasonal index. If you add them, what do you get? We get the value 12, right? So we will have to make sure that it reaches it basically adds the indices are such that they add up to 1. I can't help feeling that there is something incorrect we're trying to do. Did we miss any step? So we have the values coming from the regression, then we did a deseasonalization. Post the deseasonalization, these values themselves are summed up every season. Oh, okay. Can anybody tell me what is the mistake that I did? I actually made a mistake. I'm sorry about that. Yeah, we cannot calculate the detrended values here. It can't be done here. That's the issue. We can't get it done here. It needs to be done in the pivot table itself. I'm just going to refresh it. It will show blank. Yep. Go to analyze. Go to here. Go to calculated field. Use this field, monthly beer production. I think it is. Yeah, deseasonal values. So what happened here is, if you want to understand what took place here, just bring these values here, you'll probably get it better. So 497 divided by 611, that is what you're looking for. Why? Because in 1956 H1, the actual beer production, if you sum it up like that at a seasonal level, it is 497. And then you divide that by 611 to get the index. So it comes out to be 0.81. Sorry for the back and forth, but did you guys follow what happened? Just made sure that we don't do anything incorrect. Can you please let me know if it is if it's clear what happened here? Hello? Anybody? Any doubts on what I just did?
Haritra, is it not the same? Like we have to try to do y divided by y estimation. So I mean, what is the difference here you did like last time and this time?
Because last time the detrending I did at an individual level, but that is not what you need. The detrending.
Okay, this one in quarterly, like 6 month level, right?
Yes. So you have to roll up the data at a seasonal level and then do the detrending.
So that means you just add the 6 month data of the YT divided by addition of Y estimation of well, right? That's
Yeah. So yes, I will add that comment here. Okay. I will add that comment here in the deck when I upload this. I'll upload this again. What I'm going to do is from the drive here, I will remove this module. I'll update this statement and then I'll put it back, so that we are when you guys refer to the deck and try to do it yourself, you should not get stuck. Fair enough? Fair enough, guys?
Yes.
Okay. Okay. Now, because in the pivot table now what we have is we have the data rolled up at a seasonal level, you know, and then at a seasonal level itself, we are saying, okay, tell me the total actuals and tell me the total estimate. I'm going to divide the total actuals by the total estimate to get my deseasonalized values at a segment cross year level. So that's what we have. Now in this scenario, and this is exactly matching with what the content is trying to say, that we'll have 16 data points. We'll have 16 data points. That's it. Because of a quarterly 32 that we had. In this case, we'll have 19 data points. So if we just go here, we have 20. Yeah, because we've taken 1975 as well. It's okay. We have an odd number of years. We can either have 19 or 20. In this case, I can't really help it. So let's have 20, not a problem. So I'm just going to keep it like that. But basic seasonal index, this is important. Why? Because remember we spoke about it yesterday that seasonal indices should add up to 1. But both the seasons they should be like 1. So if you just sum it up, it is a little bit above 2. See, 2.64. So what I'm doing is I'm saying I'm going to take this number, divide that by the sum, which is 2.64, and then multiply it by 2. That adjustment I'm trying to do. Over here again, you take this number, divide that by the sum of it, and then multiply it by 2. Once you do this, you will then see that they both add up to 2 because you have 2 seasons. Okay, so just so that you are able to recall, we have done this in this module. I know sometimes it becomes a little bit of a back and forth, but it's good to go back and check. Only then, not only will our memories be refreshed, but also we'll be like, yeah. So now this is what we did, right? Remember we had 4 seasons and we had 3.974, and then we adjusted them so that they're like out of 4, then what is the index? So they now will add up to 4. So the indices will all add up to the total number of seasons. That's what I have done here in the Excel also. Where am I? Where? Oh my, okay. So now point final.
What is the adjusted R square and R square value?
Where did you find adjusted R square?
I'm saying how to find out that.
Oh, how to find out that? Yeah. How to find out is basically go to the data analysis tool pack and run the regression. So it will calculate it for you. So if you see this, right? Yeah. So when you run the regression process, it will calculate all of these outputs for you. So the ANOVA table will come, the R square value will come, the adjusted R square value will come, everything will come. Did I answer your question?
Oh yeah, I just can do it now in this method.
I just did a little while ago. Okay, I'll show you. Okay, no problem. So I have I'll go to data, then I'll go to data analysis, then I go to regression. Over here, as you can see, it's already pre-filled because I just did it. So in column D, I'm choosing 93. Column D, the first data point is at 7th row. Yeah, I go to row number 244 because in 244 you have the half the data covered because we use half the data. That's the rule of thumb we follow to calculate. So once we do that, just press OK and that's it. Automatically done.
Okay.
Perfect.
Yeah.
Just try to do it at your end. I mean, this Excel sheet is extremely it's built in a very agile manner. It's very templatized. You can try to just plug and play with the numbers, and you can get a sense of how things move, how the numbers are moving. All right. Okay. All right. So now we are at a stage where we have final seasonal index calculated 0.97 versus 1.03. As suspected, they are not playing a big role. Now, going back to the regression output, to Kamal's point, the regression output is over here. So we've got So Kamal, as you can see, we've got like the intercept here, the growth rate here. Now we
Yeah,
also
sure.
have the seasonal component calculated. So we have everything we need to progress with our forecast. So this is all that I kind of wanted, the basic initial estimates. So this is my initial estimate for the level. This is my initial estimate for the growth. These two have come from the regression model. These two are going to come from the, essentially the seasonality actually. So for H1, H2, it's 0.97 and 1.03. So let's just say it is 0.97 and it's 1.03. Yeah, these are two initial seasonal estimates. So now what is happening? I'm also going to refer to the deck so that you're able to follow what's going on here. L0 plus B0 plus Sn, the top one. So this one is, if I'm calculating the level estimate here, this is going to be L0 plus B0, right? L0 plus B0, this is alpha times the value given here is the original time series value divided by the fundamental, the first seasonal index, 1 minus alpha plus the L0 plus beta 0. So that's how we get the level estimate updated. Where do we see that in the content here? It's right here that L0 plus B0 yeah, so 98.56 is coming here, right? So yeah, so this is where we are coming from. So alpha equal to 0.2, this is the scenario here. Just allow me one moment, I want to check one thing. Yeah, okay, so correct. The forecast made in the first step is actually L0 plus B0 multiplied by seasonality, and we find that to be described here. For a second there I got a little lost, my apologies. So the L0 plus B0 is basically the the level and the growth, and then the first seasonal value is being multiplied to calculate the first point forecast of Y1 from time t0, from the initial values, right? So you've got this value. Now what is if you just notice how the forecast is happening, it's happening for one period in the past, and you're trying to compare the effectiveness of the model. So in this section, we will just use the previous value. In this row, we'll use the previous value. And then when we go to row number 3, we'll use the previous value and so on. So over here, we are just using L0 plus B0 multiplied by that seasonality. But in the next row, when we move to this row, when we try to forecast, we'll have to update the level and the growth estimate and also the seasonal values. This is where we come to step 4, where we are saying we will use these constants, and we'll start with the level actually. So we say alpha multiplied by the detrended value plus 1 minus alpha multiplied by the addition of L0 plus B0. So we've got 75.57 coming as level estimate, updated level estimate. The updated growth estimate is going to come from gamma plus the difference in levels plus 1 minus gamma multiplied by the previous estimate. So its previous estimate is 0.34. So it's quite simple. It comes here. Then comes seasonality. So seasonality is also like the constant here, right? Multiplied by the detrended value. So we have 93.2. This is the new level estimate. So I can just say that, this is going to be the detrended value plus 1 minus constant, which is 1 minus delta, multiplied by the previously estimated. Now this is an error in the formula, so it has to be this. Yeah. So I think, yeah, we are now good. So we have these three. Now once we have these three, we can then proceed and do our calculations. quite smoothly and then proceed to check the efficacy of the model. Now, when we try to look at the effectiveness, so where were we in the double exponential smoothing stage? Let's just go back and check. We were at a stage where alpha was 0.1, gamma was 0.35. So if I bring those constants here, right, then what happens? Let's have a look. RMNC actually goes up. So error in it becomes worse for the model, right? So it doesn't really help much. In case of smoothing constant, say I do 0.2, it actually becomes more worse. So if it is 0.1, that is fine. I guess what we will probably have to do is keep alpha as 0.2 here and gamma as 0.1. Then we are bringing it down to 21.36. But at the same, I mean, looking at these numbers, it says that clearly the RMSE value in case of double exponential smoothing is turning out to be a better one any which way. So a little, double exponential smoothing is clearly on top, and then comes the simple exponential smoothing. Holt Winters is not able to add a lot of difference, is not able to bring in that much improvement in the scenario, and the reason is very simple, that the seasonal impact is not that much strong. 0.97 is very close to 1, almost 1. So therefore it's little or no seasonal movement, although from a graphical perspective it looked like there is the case. But even then, purely from a fit perspective, if you look at the fit, then the Holt Winters is making more sense, and I'll show you why. Let's bring in all the graphs together. So let's have this graph, which is this particular, this is the the Holt Winters graph. So if I do first, I'll get rid of the trend line. I will just remove this trend line. I'll recalculate or bring it back in actually. So let me try to also see if I can reduce this to some extent, the RMSE. It looks like it's not going down any further unless we bring it to this stage. So if we keep the dampening factor or the alpha factor to be slightly lower, this can actually probably be better. Yeah, see, the RMSE value is interestingly connected to, so very related to smoothing. If you just smoothen the value as much as you can, then you can get the RMSE value, but the fluctuations are lost. If you can, I don't know if you are able to follow the graph changes. If you just, is my screen too small for all of you? I think it's fine now, right? Can you just follow the blue line and see the fluctuations? So if you keep 0.1, the fluctuations will become, it will become sharper. Then again, the growth, this becomes like this. But again, if I try to reduce the constant, the graph becomes much more smooth. So if I just say 0.3, can you see it has started capturing those seasonal peaks also? Your forecast values are also starting to show extreme high seasonality, and that is there. So say you increase it to 0.8, you almost replicate the original graph. Can you guys see it? So now let's keep it at 0.2, 0.1 and 1 as best practice, and let's see where we net out. If you want, you can probably keep this as 0.09. Yeah, let's just stick to this one, and let's see how much R square do we get. Yeah, it actually becomes a little worse from a fit perspective. So somehow the idea is that the double exponential smoothing graph is definitely a better graph in this scenario. You may or may not want to consider seasonality as an option, because although there is some element of seasonality, but there is not a lot of strong seasonality in the data. So that is what we can conclude from this analysis. However, you should be practicing more and more, because there are a lot of data sets I think available on the internet based on, this is one source I can show you, UCI data. Yeah, UCI machine learning data repository. Some of you may already know this as a good source for data, but you can click on time series, you get 44 data sets. So there is a lot of practice material out there for all of you to sort of start working. Pedestrians in traffic data, you can see how many data points you have. Instances are given here. So if you want to sort it, sorted by instances, you can see the really big ones come on top. Okay, human activity recognition. Yep, it's right here. So you can also use for machine learning, you can use for time series, but yeah, time series, if you want to use for time series, just keep one column and study the time series. It's a multivariate data also, and it's also a time series data because it's given across time.
Can you send this link?
This link?
Yeah.
This link, okay. Do you find this interesting?
Yeah, too much.
Too much, okay. All right. So that kind of brings us to the close of the agenda today, where we have looked at this. Let's have a glimpse of the code in Jupyter. In order to quickly do things, you can use the template. Please feel free to modify the numbers and play around with the numbers. Okay. So did you find today's session to be useful and somewhat clarifying in terms of exponential smoothing? Because that was the intent, that we conclude today with respect to everything connected to exponential smoothing, and we are sorted from a theory perspective. So we are good to move towards coding, and then we will look at ARIMA, a little bit of ARIMA theoretically, but more from a Python perspective. So that way, I don't know if you guys are, sort of actively going to consider time series as a specific use case for your jobs or roles that you will be taking later on. But I don't have a lot of time series related projects in the kind of role that I am. Most of the work revolves around supervised and unsupervised. But series you've covered enough to
sorry to interrupt you, one question. Yes, so hello.
Yeah, please go ahead.
Yeah, okay. So we are actually using linear regression, right, to find out the estimation, right?
Correct. Yeah.
Yeah. So is it possible to use like different regression model to find out the estimation and then try to see, because data is not always linear, right?
No.
So you can see we got always like 70% like that. We got, because we can expect more also in case of linear regression.
Right. You can. So, you definitely can. Just that when we it's an initial assumption that we're taking, that if the structure of the model is beta 0 plus beta 1 t, then it is a linear form that I'm assuming right away, and I'm trying to see how much can a linear model explain. Now say your r square comes out to be 10%, 20%, it's very low, right? Then you may want to sort of try and see if you can use polynomial regression or something else. But you cannot use any machine learning regression, because you will not get a slope. It has to be a statistical regression. Only then you'll get a slope.
How about decision tree regression?
Decision tree does not calculate or give you estimation of any slope or intercept. No equation is built. That is the basic difference between machine learning and statistical modeling. There is absolutely no equation built in any of the machine learning techniques, guys. Always keep this in mind. This is a very strong interview question. Can you please explain? This is the question. I keep asking this question a lot, that what is the difference between statistical modeling and machine learning modeling? The basic difference is that in all statistical models, you assume there is an underlying probability distribution of the dependent variable as well as for the independent variable. That is the first thing you throw out of the window. When you do a decision tree or random forest, you take the probability distribution assumptions, pack it in a bag, pack it in a box, and you just throw it out of the window. You don't care about it. Second thing is, in a statistical model, you build a functional relationship between the dependent or the target and the set of independents. That functional relationship is what we call as a statistical model. In a machine learning scenario, you take that concept along with the distribution assumptions, you throw that also out of the window. You do not care about a functional relationship. You just want the machine to create decision boundaries and build those rules within those decision boundaries that it will help the machine or the algorithm to classify people, or say find out the average value. So if you were to use, say, random forest, okay, what is that going to do? It will create many weak learners for you, many weak learners. And in case of classification, you're going to take the voting of how many weak learners are saying that it's going to be in class A. You take that majority voting, you just classify in class A. In case of regression, it will say, okay, what is the average predicted value from all the weak learners? I will take the average of all the predicted values from the weak learners and then call that as the average for the average predicted value using my random forest regression. But it cannot tell you what is the relationship, what is the functional relationship. So if your project manager, if your business leaders are expecting you to come up with a functional relationship, your hands are tied. You have to do a statistical regression. You have no option, because otherwise your regression coefficients cannot be captured. You would not be able to do. So what you can do in that situation is that you can use a decision tree to figure out what variables or what features are coming out as important, and then use those features to go to statmodel.api or go to scikit-learn also. I think statmodel.api is better because it gives you all the regression coefficients there. So just take the intelligence from scikit-learn, apply it on stat models, and then get the job done in case you really want to build a equation-based model. I wanted to elaborate on that because it comes across in many interviews that, you know, what is the difference between and people are just trying to see if you're clear on the concepts. I hope that was helpful to some extent.
Yes, sir. But one more question comes up is that I saw one article where they're using LSTM for the time series prediction. Is it right?
Yes, you can use a long short-term memory. You can use Facebook Profit. Those are within the time series. So when you combine deep learning and time series together, you get things like LSTM. You get things like I think Profit is not all about deep learning. I'm not sure how Profit works, but purely from a subject perspective, if you're trying to learn time series for the first time, you should start from basic forecasting, study ARIMA. That is within the scope of our discussion. LSTM, I think, will be a part of your deep learning discussion, so you can take it up there. But yeah, the short answer to your question is that yes, you can also apply LSTM in order to get your time series forecast. So we have a short Python code. See, you over here, I'm trying to decompose the trend value, the seasonal value. There are packages to easily do that. Statmodel.tsa time series analysis API pretty much helps us. In case it's a simple exponential smoothing, this is how the output looks like. We also can do Holt exponential smoothing, and the output will change. We can also do seasonal Holt. Seasonal periods are mentioned, and the output will actually look even stronger. And these are the predicted values or the future values. So it's not, I mean, it gets a lot simpler when we actually use Python. But yeah, if you're really interested to know the formula and the calculation behind it, that was the intent, to show how to do it in Excel. Because and then we have the concepts of stationarity and how to stationarize the data using first differencing method, the autocorrelation, and the ARIMA model results. So yeah, we will look into each one of these things in a detailed manner when we meet next Saturday at 3 o'clock. But I guess we are leaving today with with a strong sense of what exponential smoothing can do, how it all comes together, how the process actually works. I hope that that part is clear, right? That is the objective. That was my objective today. Okay, so I guess we are good then, right? For today, then I'm going to update. Yeah.